Okay, I think I can get started. It's a great honor to be here in Chile. I thank the organizers for inviting me. Astronomers visit Chile quite frequently. Your country has some of the most amazing landscapes, but also the best skies in the world. But I'm not only coming because you have the best skies, also coming because I collaborate with Chilean scientists in my field. And furthermore, some of my former collaborators from my institute are now professors at Chilean universities. Astronomers are used to reconstruct the history of the universe. During this week, we will talk about the future of Earth. And about 20 years ago, astronomers found the first planet around a solar-type star. Now we find actually terrestrial planets, and we can place our solar system in context. 20 years later, I actually can show you not only indirect evidence for a planet, but I can show you an image. So that is actually an image of a planetary system with 4 planets. The light of the central star is blocked because it would be too bright. And this planetary system contains planets we do not have in our solar system, so-called super-Jupiters, which have masses of about 4 times the mass of Jupiter. On top of this object is actually very young. Young in astronomical terms, it's young, a couple of million years old. Our Sun has an age of 4.567 billion years. So remember a number, age of the solar system is 4.567 billion years. This is a very young system, and it's completely different to our solar system. Just let me remind you that for centuries, even millennia, we only knew one planetary system. All our theories were calibrated with this planetary system. A physicist, and I'm a physicist, would call it the ill-posed problem, because you cannot compare this planetary system with other planetary systems. And you see, in our solar system, the giant planets have to be far out because the temperature is low. We know that this has to be the case. And the terrestrial planets are inside. You already have seen that this is not true for the image planetary system I showed you. So where do the stars form? That is actually a picture taken at the Chatnatur Plateau at 5,000 meter altitude of the Milky Way. And if you go to the northern part of Chile and enjoy the wonderful skies, you will actually see holes in the sky. And the famous astronomer Herschel interpreted that as places which are empty, which do not have stars. But he was wrong. These are actually clouds of small particles which are blocking the light of the background stars. And we call these objects today molecular clouds because they contain molecular hydrogen. So if you observe the Milky Way, you actually will see the birthplaces of stars. This is one of the birthplaces of stars in the Rhine molecular cloud. You see this wonderful filament at long wavelengths, and the background image is an optical image showing you the famous Orion Nebula. These objects are actually the coldest objects in our galaxy. And they are the most massive objects as well. They have a mass of million solar masses in temperatures of 20 K, and you see here this filamentary structure. Now we observe the total galaxy, and we ask the question, how many stars do we form? And we know that we form 1 solar mass per year. Only 1 solar mass per year. And because most of the stars are similar to our Sun, we form only 1 star per year. So a low birth rate compared to humans on Earth. So this is another number you should take away. 1 star per year we form in our galaxy. I told you that most of the stars are actually like the Sun, but there are a few stars which are very massive. So this is actually an infrared image, and here you see one of these massive stars in the center, IS-5, which actually is not a single star, but stars like to live together in social communities. And the star has a mass which is very large. Why are these massive stars actually interesting? So I show you another one, and the star we discovered here has a mass of 100 solar masses, and the luminosity is 1,000,000 times the luminosity of the sun. So this is really a very, very massive energy power station in the galaxy. On top of that, these stars produce metals. Astronomers mean with the word metals everything which is heavier than hydrogen and helium. Iron, calcium, everything which is in your blood, in your bones, was once produced by such a star. So all of you here are actually stardust. So all the atoms, if you talk about the origins of life and biological systems, all the atoms were produced in stars. And therefore the massive stars are important. Let's imagine we are sitting in a cold cloud at 20K, gravity takes over, the cloud collapses, and at some point density is high enough that you form a disk because you're like a ballerina, and the physicists would call it angular momentum problem. The mass can easily flow along the axis, but in that direction you have centrifugal forces, and you form a disk. Isn't that a great cartoon? Do you believe me? You shouldn't, because that's a cartoon. I should actually show you data. So this is a structure of a disk as we took it just about 6 months ago with a very large telescope of ESO. We are using a planet finder instrument we built for the European Southern Observatory, and the resolution you can read here is of the order of 20 to 100 AU. And that is not a spiral galaxy, because you see spiral arms. It is a disk, and this disk structure is triggered by embedded planets. Now, how do we do that? You see this flickering here. So if you go out in a starry night, you will actually see that the stars also flicker. That is bad, because we are building a large telescope like these 2 or 4, and you see Melipal in the Mapuche language, that's Southern Cross. You see Yepun, that is the evening star. So we honor the Mapuches here in Chile with the names of the telescopes. And then what we do is so-called adaptive optics. Imagine, as a photon, you have a Planck parallel wave. You travel for centuries with light speed from the distant corners of the universe. In the last second, you have to cross the atmosphere, and the atmosphere destroys your Planck parallel wave. And the stars flicker. And we don't want the stars flicker, because then we have this very strange image what we have here. So what we do is we take a little device, we call it adaptive optics, and we change the wavefront again to Planck parallel one. So do you believe me? You shouldn't, but now I show you a little movie. So that is how the stars dance, and now I switch on my device on a young star and actually see a very sharp image and see 3 stars instead of 1. So that is how it works, and in other words, you collect light now, and here is the adaptive optics system. You collect light on a very small space, and if the system is off, you get this flickering image. So we now get images which are as good as images from space, and at some point, and that is done here, we combine space and Earth and actually find that structures in this disk move with a very large velocity, with a velocity of about several kilometers per second. You will never get this velocity in Santiago, especially not in the morning. I think in the morning we have in Santiago velocities of about 1 millimeter per second, but I offer you kilometers per second. So this was actually my first trip, or one of my first trips to Chile to find such disks. I used a 22-meter telescope. The old Swedish, European sub-millimeter telescopes no longer in operation. Traveled to Chile, had observing time, and was looking for the emission of this. And wow, I came back as a young professor and could write a paper, which was actually the first survey in the southern sky, and determined the mass of these disks. And the mass is 10 to minus 2 solar masses, or 0.01 solar mass, and that is sufficient to form a planetary system. Then I also found out that actually the particles grow. The particles are very small at the beginning, 1 millionth of a meter. We call it a micrometer. And we found that they already grow to centimeter sizes. That is just the beginning of a long process. And now here we are, many years later. This is now 20 years later from my first observation of unresolved disk emission. That is an image which I think will be one of the most famous images in science and in astronomy in the coming years. That is a resolved disk with ALMA, and now we actually see gaps in this disk created by planets. So sometimes, if I'm lazy, I'm not going to an observatory, I write a little code. This little code is one of the largest which is being used in astronomy for simulations, and it actually shows you how such a disk would look like on the computer. So from time to time, we switch our technology from the telescope to the computer, and that's one of the most demanding simulations which ever have been done. The problem is you start with these very small particles, and you have to end up with planets. You start with 1 micron, and you end up with a kilometer. These are 10 to 12 orders of magnitude in size, and 10 to 36 orders of magnitude in mass. So this is a bit of a task for nature, and now we think we know how it works. So the first mechanism is very easy. These two particles come together, stick, and grow. Fine. If you have a planet, then gravitation helps. Gravitation brings the particles together. But if you have a particle which has the size of a meter, it does no longer care about the gas it is embedded in, gets high velocities, and if you crash with high velocities with a ball against the wall, you will not grow. So there's a puzzle. Why do you grow if you have this meter-sized barrier? And we thought, well, at some point, if your particles spring together, then gravity may take over. And that is demonstrated in this simulation here. So what you see here is a disk from above, and all these points are actually particles in a turbulent gas. And normally, the material would be sheared away. But what you see here, there is this little point which accretes matter and is not sheared away. It's a dust cloud which is held together by gravity. It's not sheared away, it's getting mass, and it's forming a planet. So we found a new mechanism how it could work. And that would be then a young planet accreting and getting its luminosity by accreting of matter. So now we can actually play what Kant proposed in his famous book, Gebet mir Materie, ich will eine Welt daraus bauen. Give me matter, and I will construct the world out of that. So I now play God, and that is the distance from the sun, and that's the mass of the planets. Now you see what happens. These planets are not staying there. They're talking to the gas. They're getting mass. You see they're going up here. They're getting more mass, and they migrate inwards. So in other words, young planetary systems are not boring, they're very active, and they like to play. Let's, at the end, discuss a little bit water on Earth. So when we came back from the south of Chile yesterday and looked out of the window, everything was covered by water, and we're used to that. 80% of the surface of Earth is covered by water, and we call it the water planet. But that's wrong. It's not a water planet. Only 0.02% of the total mass is actually in water. And if you would put all the water together of this Earth, would have this volume. So we are not a water planet. We have very little water, and we should be careful. We actually find this water also in these disks I talked about. So all these little bumps here are not noise. They're all the signature of water in a disk. But we not only find water, we find organics, HCN, smells very strangely, C2H2, all the components which may at some point form amino acids in a meteorite and may be brought to Earth. Earth could have started dry, started wet. Today we know that the Earth started dry. And then we had to bring water to the Earth from comets and asteroids. So at the end, let's come to a spectrum, to the new frontier, and I think Lisa will talk more about that. And it's always good to have a former friend and colleague, because Lisa was a group leader in my institute for a while before she decided to move to the US and build her own institute. So it's always good to meet friends. So what I show you here is actually the image of an exoplanet spectrum. Now, this is a wavelength here, and that is the spectrum of the exoplanet. We can now do that. We can get a spectrum of a planet. And if you don't believe me, here is the spectrum of a planet produced by another technique. We can determine how much water is in the atmosphere, and we can do that in the future also for terrestrial planets. So our future as astronomers is actually very bright. We are in a very privileged situation. We should be very thankful to the taxpayers to allow us to have our hobby as a profession. This is a luxury. And you see here two projects I'm actually involved in. I'm a co-PI of an instrument we built for the James Webb Space Telescope, which will be launched in about 2 years from now, fingers crossed. It's actually the most expensive project astronomy ever did. Was also criticized because of this, but now we are on time and budget. And then we have another project we just started, the European Extremely Large Telescope in the northern part of Chile. And I should really thank the Chilean people that they allow us to bring such a high-tech machine to Chile. And I can tell you that the environment is really fascinating. So I was visiting the place last November. Everything is prepared, and we will bring all the high-tech material to Chile, and we will involve Chilean companies to make it happen. So in 6 years from now, or maybe a little bit longer, I will come back and we will inaugurate the telescope, and we will celebrate with the Chileans the first light of this instrument. So I'm very proud that I'm part of these two projects. I'm also the German representative in the ESO Council. So we made all these political decisions, and you can imagine that it takes time. You have to find the money, but now we go, and you will see this telescope. The future is actually now. It's very similar to the slogan of the meeting, and I'm telling this because astronomers now have the best facility in the world to study planet formation. I showed you an image. It's called ALMA. It's actually at a place where you have a little bit of oxygen problem if you go up too fast. It's one of the most beautiful places on Earth. That shows you the telescopes up there. It's in full operation now. I have my own programs, and that leads me to a big thank you. And in the back, you see two transporters, which actually have German names because they were produced in Germany, Otto and Lore, and I'm standing close to these transporters, transporting the antennas to another place, reconfiguring the big machine. Thank you.